Okay, so let's start the third lecture of Professor Laura Tolos. And okay, thank you.
Thank you.
Laura.
Thank you, Ignacio. Thank you. So, yes, well, today actually, I'm going to start talking about hypernuclei, just a couple of slides, because I was supposed to talk about this the first lecture, but we didn't have time. So I think now, yeah, before getting into hyperons in matter, I should first talk about hyperons in a hypernucleus. So basically kind of a few body system where a hyperon sees few other nucleons, okay? So yeah, hypernuclei, as I mentioned at the beginning, I go back to the beginning of the lecture that you already know, sorry. It's basically this idea, right? That you have a hyperon, which is substituting, you know, one of the nucleons inside the nucleus, and therefore you have this bound state of nucleus, of hyperons in nuclei. What are the different, now I'm going back again, sorry, because I'm going so fast now. This you already know everything perfectly. So here, so what are the different production reactions of this kind of hypernuclei? So there are different ways that these are being produced. So I'm giving you, you know, a main idea. So there are what they are called, the first one to think is this lambda hypernuclei. And therefore you have what they are called strangeness exchange reactions. What does this mean? That you start, for example, from a kaon beam, which actually kaons are quite slow in order to be trapped and to be bound with nuclei. And the idea of a strange exchange is that you, as I said, kaons interact with nucleons inside the nuclei. So this will be K minus, for example, interacting with carbon. And one of the S quarks, okay, that belongs to the K minuses is exchanged, you know, from the meson to the hyperon. So you form this lambda hypernuclei starting from K minuses. So you can see this exchange here using, you know, the quark structure of these mesons and baryons, okay? So then, you know, actually the non-strange part is now being part of the meson that is created. So you have reactions, as I was saying, K minus going to interacting with carbon and giving rise to pions, and now a carbon nuclei with a lambda inside, okay? So reactions of this type are indicated here. So basically this means that a neutron interacting with a K minus is giving you Pa minus and a lambda. And of course, you could also think of having, you know, a sigma minus and plus also in the final reaction, okay? Now, this would be a strangeness exchange. And as I said, you have to lower the momenta of this K minuses, this beam, in order to generate, you know, that these K minuses see the nucleus, and then something, you know, like the lambda is bound to nuclei. There are other ways of producing lambda hypernuclei, and this is associate production. So the idea here is that you have a beam of pions, okay, so no strange particles in the incoming particles. So a pion interacting with a nuclei of a nucleus of the, with a nucleon of the nuclei. And what you have here is that you form these pairs SS bar in the final state. So basically, you end up having two particles with a strangeness, one with a strangeness +1, and the second one, and the lambda with a strangeness -1. So this is this reaction, pi plus interacting with a carbon, and gives rise to these K pluses, and then a lambda, which is created, and it's bound in the carbon. So compared to the previous reaction, those have the advantage of having pion beams which are easily being produced. So the intensity of these beams is larger than in the strangeness exchange. The only thing is this kind of reactions where you have here the creation and annihilation of pairs is less, you know, the cross-section, the production cross-sections are smaller. So you have the advantage of having more intense beams, but you have the production cross-sections that are smaller. And a third way of producing this lambda hypernuclei is through what is called electroproduction. The idea here is that an electron interacts with a proton, for example, of the nuclei, and this interaction is understood in terms of an exchange of a virtual photon. So basically you have this virtual photon interacting with the proton and giving to a K plus and a lambda. Okay, so you know, an entering electron leaving another electron with another momentum, and then in this photon exchange is the one that is, you know, giving rise to this reaction. So the reaction I mentioned is an electron going to a carbon and then an exiting electron and then K plus and lambda, of course, these two in order to conserve strangeness. So this, again, I mean, having an electron beam is easier and more intense than having pion beam and more than a K minuses. But again, the cross production cross sections, for example, this electron production is 2 times smaller than the associated production. So there are different facilities and different ways depending on what they have access to and which kind of beams they are analyzing. So for the electron production, there are experiments at JLab, Jefferson, oh, they were at Jefferson Lab. Then MAMI-C, which that's mines, and associate. So you can have them, or they have had them, you know, in the Keck in Japan and BNL in the States, and then a strange change in Finuda here in Italy, and then also in CERN, BNL, and Keck. This is for lambda hypernuclei, and actually these are the ones most abundant. Okay. Things get more complicated as you try to get more, you know, hyperons into the nuclei. And this is, for example, but still we have few hypernuclei with two lambdas, for example. And those are, I will show you the chart later on, but one of the possible reactions is actually what it was, you know, proposed for Panda at GSI at FAIR. And the idea was to have an anti-proton beam, okay, that interacts with the nuclei, with this carbon. And then you have exiting particles with strangeness, for example, kaons or anti-cascades. And you form a particle with 2 strange quarks, the K and the cascade minus, okay? And this cascade minus is captured by a second nuclei in the atomic orbit. And this allows the reaction of cascade into one of the nucleons here to give rise to 2 lambda, and that are bound in this second nuclei. Okay, so this is the proposed mechanism. Of course, this is a similar mechanism that instead of having, you know, this cascade decay into 2 lambdas and those 2 lambdas being bound in the nuclei, it is also possible to actually have this the cascade hypernuclei. So cascade, for example, in beryllium. And you can think of reactions of that type, or reaction, for example, involving K minus a proton, and then you have a particle with 2 stranges, and then the K plus, which compensates, you know, the 2 strange composition of this cascade. So in this way, these are some of the reactions, not all of them. The older ways of producing are what they are called emulsion data. But these are reactions that are being taken into account in order to create this new chart of nuclei. So this chart of nuclei, I already showed it to you the first day when I was motivating why to study hyperons. So you have here, you know, what has been produced, okay, in the lambda hypernuclei. So you have hydrogen with a lambda, helium, lithium, beryllium, boron, carbon, nitrogen, you know, and oxygen, and even higher ones. I don't even see them here. Aluminium, I think. And then, of course, now the idea is that the different colors is different reactions, okay? So the green ones are in this electroproduction. The white ones are gamma ray data that I didn't talk about actually. And then the blue are from this strangeness exchange. And the others, for example, these ones are from associated production, okay? So now, as I was saying, not only this lambda hypernuclei, but also these 2 lambda hypernuclei are in helium, in beryllium, in boron. So as you can see, we are obtaining, and nowadays is a field of research and very interesting research on getting these hypernuclei in order to get an information on hyperon-nucleon, hyperon-hyperon interactions when you have 2 hyperons, of course, the decays, all these are unstable, so they will decay, okay, into the hyperon. So it will give you an information on the hyperon nucleon going to nucleon nucleon. And of course, per se, they are interesting because you have a new set of nuclei, okay, and then you can have a study, you know, the different hypernuclear data, okay, so the structure of these nuclei. So as an example, I mean, there is a lot of hypernuclei, I mean, a lot more than what I'm telling you right here, but few things that are interesting, actually. The first one for neutron stars are this binding energy of lambda hypernuclei. So here you see the binding energy as a function of the mass number. Well, it's a function of the mass number to the minus 2/3. So the idea is that as you move in that direction, so you move to the right, to the left, you're having larger and larger nuclei. Actually, this is indicated by this number here. And these are data, okay, from different hypernuclei, from the different states, okay, the different levels, energy levels of these lambda hypernuclei. And the interesting thing is that actually with the continuous line is some single particle model that by Gall and collaborators that fits pretty well, okay, with these results. And let's say for the physics of neutron star, is interesting that more or less, you know, they seem to saturate, or they go to this 30 MeV of binding energy. So this is this minus 30 MeV that later on, when I discuss neutron stars, I think I said, I will, if not, I will show you again, is this minus 30 MeV that when we discuss about interaction of lambdas, of binding energy of lambdas in an infinite nuclear matter, people are discussing about, okay? So this is this minus 30 here. And something also very, you know, fashion, let's say, these days or these years, is the hypertriton lifetime puzzle. So in a few words, you have the lambda, which is binding in nucleus, okay? It turns out that this binding is not too big. I'm talking, I think, about KVs, okay? So this gives you an idea that the wave function of the lambda that is modified, I mean, this modified wave function in the nucleus is not much modified, okay, as compared to the free one. So this means that the lifetime, okay, of these objects with the lambda will be similar to the lifetime of the lambda, okay? So it's not much the binding here. It turns out, I mean, this is the lifetime, okay? And these are different observations or results, experimental results. So one of the latest one, it was this 2018, which was from the STAR experiment, okay? So it turned out, you know, that you can see that one of the most recent ones was giving a lifetime smaller, okay, than the expected lifetime, okay, of the lambda in the nucleus. So there was this puzzle, okay, that you were expecting, and actually these are different lines, are the different let's say predictions, okay, of models, of different models. And then you see, you know, that there was some discrepancy here. So actually Alice, more recently, and maybe in last year or the year before, I don't know exactly the year, it was going back, you know, to this value that we were expecting. So these conflicting measurements, okay, between STAR and Alice, then triggered again a lot of, you know, a revived experimental and theoretical interest on this hypertriton lifetime. Okay. Somebody raised a hand, I think.
Yes, there is a question. Please go.
Yeah, it's me. Sorry to interrupt.
Yes.
About the binding energy of different hypernuclei as function of the mass number. I was wondering why, if the mass number grows, the binding energy raise and then saturate.
Well, I mean, it raises because it's telling you that the interaction is getting more and more attractive. Okay, so somehow the interaction, this is what it means. Okay. Why you were expecting repulsion? In this case, you can see that it's getting more and more attractive. You see more nuclei, and you know, this is what it's telling you. Why it saturates? I don't know if there's a reason. It's just a trend that you observe. Okay, that you observe that as you get, you know, to a nuclei of 208 mass number, the thing, you know, is going towards kind of a maximum. Okay. Maybe it's because I'm thinking right now out loud, okay? Maybe because of the finite range of the interaction, the strong interaction, at some point it has to saturate. But this is just, I don't know. I don't know. Maybe.
I think, no, I think that the value which corresponds to the 30 MeV is the extrapolation to infinite system.
Yes.
Nuclear matter with just one lambda.
Yes.
So in infinite system, you do not have finite size effects.
Yes.
Surface, the shell, and this is the infinite system limit. Just that, I think, Laura.
Yeah, no, but I was maybe yes. That's
but I don't know if.
Yeah, this is the infinite, like in the mass. Yeah, exactly. Like in nucleon, you have this bulk term, okay, and this is the infinite. I mean, this is that term here. Why is minus 30? Well, in case of nuclear matter, is minus 16. Okay, so this is that. And then for explaining, of course, the nuclei, you have to add all the different corrections, as Ignacio was saying, okay, surface and so on.
Okay, so, go ahead.
Yes.
Okay.
So, okay, and this is just to show you that that the different experiments that you might have, okay, that are working on hypernuclear experiments, okay. So you have several of them, you know, here in Europe with the Future Panda, then this Hype in GSI, then we have MAMI, then we have Alice, also LHC, and Finuda in Italy. And so a few of them also in the States, one in Dubna, and then also very interesting, you know, let's say, laboratory or people really working on, you know, in Japan, which is the KKEC and going to JPark. Okay, so this is kind of the future, which is now coming. Okay, it's already working. And well, here you can see, you know, the time evolution from the 2010 or even before to the 2020, where Panda actually is still not running. So this should be moved somewhere here, you know, hopefully in maybe 5 years, hopefully. And of course, I mean, this is experiments, but in lattice QCD, you also can try to generate those nuclei, okay, and see their properties. Okay, this is from what I wanted to talk, actually, and I already talked maybe too much. So I'm going to move now to the lecture that this was supposed to be this today. And this is, let's share it in full screen. New share here. So I hope you see it. So hyperons in matter, okay? So the outline, it will be why hyperons. And then the idea here is I'm going to show you one specific way, okay, of constructing this hyperon nucleons, the interaction of hyperons in an infinite nuclear matter, okay? Which is one of these ab initio models that I mentioned the first, on Monday, which is a diagrammatic approach, which is called the Bruckner-Hartree-Fock approach, okay? But for that, I will have to tell you a bit of what is the many-body problem, what is the Goldstone theorem, and how this Bruckner-Goldstone theory appears from this Goldstone theorem, and the approach at the lowest order in the Goldstone theory, you will see that is this Bruckner-Hartree-Fock approach, okay? So this lowest order in the Bruckner theory will be the Bruckner-Hartree-Fock. And once you know, you've learned a bit on how to construct these interactions in matter, but I said this is a specific case, the Bruckner-Hartree-Fock, I will introduce you using this Bruckner-Hartree-Fock, how the interaction with, how the potential of hyperons, so let's say how hyperons in matter, how the interaction looks like, okay, and what is called the optical potential of hyperons, okay, which means interaction of one hyperon with the rest of nucleons. Okay, so, well, first of all, why hyperons? We already seen why, for example, we have seen already, and I discussed, equation of state of neutron star matter. I discuss right now hypernuclei, okay. And of course, per se, it's interesting because you get to know, hadron interaction in matter. And out of this, you will get to know what's the interaction of one hyperon or one hadron in the presence of the rest of them, okay? Okay, so Again, I think I showed that before, but again, just to repeat a bit of what we know experimentally on hypernucleon interactions and hyperon. So we have some information on hypernuclei that I just mentioned. And this is from scattering, okay, this is the scattering data minus that there is not so many scattering information as with nucleon. And from the hypernuclei, here is a kind of a summary. So several lambda hypernuclei, which is giving us this at infinite matter of minus 30. Then we have sigma minus atoms, sigmas with nucleons. I think one sigma hypernuclei. So, but still the question is what is repulsive or attractive? So this is kind, I put it in a question mark. And then we have cascade hypernucleus and which is nowadays giving some information of this minus 24 at this infinite matter. And these numbers here is what I'm going to show you how the theory of Bruckner-Hartree-Fock is giving or not. Okay, so how would we are in there? And then of course I'll show you also some lambda hypernuclei. So in some sense, this means that if there are nuclei, there should be an attraction. And for the other ones, it's kind of actually quite an unknown. Okay. And these are in particular for neutron stars models that people have been discussing. So density dependent models in the sense of density functionals like mean fields, quark meson coupling models, density dependent hadron field models, and more, let's say, this ab initio that now I'm going to discuss, Bruckner-Hartree-Fock, this means here, Bruckner-Hartree-Fock, also low momentum interactions or quantum Monte Carlo, okay? So I'm going to concentrate on this. So there is, as I mentioned, there are different ways, okay, different ways of starting. So in this one, actually, you start, as I was mentioning on Monday, from the interaction in free space, and then on top of it, you put the many-body corrections. And this is what I'm going to tell you, how you build your many-body corrections and how you build this approach. But let's first start, what is the many-body problem? So the many-body problem has to do, for fermions, okay, it has to do with the repulsive character, for example, of the nucleon-nucleon interaction. Okay, so we start with a nucleon-nucleon interaction just to show you this. So what is nuclear matter? I'm talking about infinite nuclear matter, symmetric nuclear matter. So I already introduced it to you. So it's this hypothetical system with the same number of neutrons and protons. And the interesting and important characteristic in order to discuss about the Bruckner theory is that it's a dilute system, and you will see why. So what means a dilute system? It means that the range of this repulsive core is much less than the distance between nucleons, okay? So the idea is that, that the range of the interaction is smaller than the distance between the two particles interacting, okay? This is the idea of dilute system. So this can be translated, okay, in terms of if you call A, the repulsive core, which is around half Fermi, is much less than the distance between nucleons, which is around 1 to 2 Fermi. So we are seeing that we have like a third, so it's smaller, okay, than 1. Now, quantities, and I think we already discussed them a bit, is the density of the system, which the particle density, not the mass density, the particle density. So it's the number of particles divided by the volume. So if you think, that the volume goes like, the radius goes like with the mass number to 1/3. So is this a typical volume that radius that you get from, which is correlated to this mass formula, okay, how this goes, you will find that actually we are discussing, here this mass number is canceled when you calculate the volume. So you end up having this famous 0.16, 0.17 Fermi to the -3 that I already introduced you on the first day. This is in Fermi to the -3. You can also translate this into momenta of Fermi, so the last level which is occupied. So by doing the same calculations in momentum space, you will get like this Fermi momenta of 1.36 that corresponds to this area 17 Fermi to the -3. This is just values that you keep in mind when we discuss about nuclear matter and nuclear matter at saturation density, which are these 0.16, 0.17 Fermi to the -3, and Fermi momento of 1.3, okay? So, as I was saying, what is the many-body problem, especially when you have two fermions, okay? When you get them getting closer and closer, basically you have a repulsion, okay? Coming basically from the Pauli principle. So, and this is of course manifest, and we have already discussed when I discussed nucleon, you know, and at short distances. So, if you think of having, you know, now that you have more particles in the system, before I was discussing two particles interacting through this potential, okay? Now, if you think of adding diagrams, you know, more and more diagrams involving this potential, so an expansion in terms of the potential, in order to do calculations in matter, this will become meaningless because of this short rate repulsion. So basically, you don't have an expansion, a really well-behaved expansion, okay? So in principle, this is not a good, in principle, okay, a good way of going when you want to describe one particle in the presence of the rest. But actually, the shell model is doing that, okay? So each nucleon somehow is independent of the other surrounding nucleon. So it moves in its own orbital, and this dynamic is independent. So you have a calculate, I mean, this is already somehow puzzling. And the idea actually is that in nuclear matter, this is represented here, is, you know, this is the potential, the nucleon potential as a function of the distance between the two nucleons. So somehow in matter, this interaction is shielded, okay, because the presence of the rest of the particles. So it turns out that when nucleons, you have many nucleons around, the nucleon-nucleon interaction is shielded, and this gives this repulsion allows, you know, to have an expansion in matter. But which kind of expansion? This is what we are going to look at, okay? And this is what I will discuss, the Bruckner-Goldstone theory, okay? So the Bruckner-Goldstone theory is a scheme, which is written here, to obtain the effective nucleon-nucleon interaction starting from the bare interaction. By resumming, you will see which kind of diagrams. So in this sense, the idea is that you resum certain diagrams, okay? And then you make an expansion using not the potential, but this resum interaction or effective interaction. So you can do kind of a perturbation theory with this resum interaction. This is the goal of this lecture today. And of course, well, part of the lecture, because then it's interesting to see how this is applied. And so this effective interaction is also called, if you have heard maybe of the Bruckner reaction matrix or the G matrix, okay? And the equation that you have to solve is called the Bethe-Goldstone equation. Okay, this is a summary of what I'm going to discuss right now, okay? Okay, so, but first of all, in order to start with the Bruckner-Goldstone theory, we have to start from the Goldstone theorem, okay? The Goldstone theorem is similar, let's say, what you already know for quantum field theory applied in a many-body system. So the idea is how to calculate the energy of the fundamental state of an interacting many-body system through a sum of different terms, okay? So starting from the energy of the fundamental state without correlation. So this is the energy of the perturbed system, okay, of the system that is interacting. And you start from the energy of the fundamental state without correlation. And the idea, I'm not proving it to you. This is the Goldstone theorem. So in order to get that, you have to, I mean, assuming two-body interactions, you have to start from, as I said, from the energy of the fundamental state and some different terms, okay? This is the expression. So basically, we will see now a couple of the first two orders. So we will start with, you have this get with the fundamental state without correlations, okay? And the idea is that you have here, this is kind of the expression of a propagator, okay? So you can see 1 divided by the energy is kind of the propagator, okay? Where you have here the energy of the fundamental state and the Hamiltonian, the free Hamiltonian, okay? And now you have here the Hamiltonian, which is two-body interactions, okay? And then you see there are different terms, okay? And then here you have the Hamiltonian of also the two-body interaction Hamiltonian. And the different terms you can see here because you have this exponential and n, and you're summing over all infinite systems, okay? And then second, you have here this term, which actually is the Pauli operator, because you have fermions. So this is preventing in this interaction from the idea here is that you start from the fundamental state without correlations, and you end up in the fundamental state without correlations. But in between, there are interactions, okay, between particles inside these fundamental states. And this is shown here with the H1 and H1. And as you have the interactions, you have to be careful that these two particles are fermions. And there, if they occupy a certain level, you cannot scatter anything that goes into this level, which is occupied, okay, which is this idea behind the Pauli operator. I will show you examples now, okay? So just don't panic yet. So, and also the idea, you know, the Goldstone theorem is that all these diagrams that you could think of, that I will show you again now, a couple of examples, have to be linked diagrams, okay? So those diagrams, what it means linked diagrams, it means those diagrams which cannot be separated into pieces by a vertical cut, which would not cross any line. What I mean is that if I have, for example, 3 particles, okay, this is this drawing here that I was lazy to do. I just did it by hand. So there are 3 particles. This means 3 particles. I will show you now what it means. They are interacting. This is an interaction line. So you see here that these 2 are not interacting. So this is not a link diagram, okay? While this one, which you have actually 2 particles, I will show you now what it means, are interacting. Here we have 2 interactions. So let me maybe show you what I mean, you know, the different diagrams. What I'm going to do right now is many-body theory, very fast. So I hope at least you get some idea. Many-body theory. So basically, fermions in a sea of other fermions. So there are different diagrams, okay, that we will discuss, but basically I will concentrate in the last ones, but that you know. There are diagrams for interactions, those you know. I mean, this is diagrams, you know, that when you only have 2 particles, this means 2 particles interacting and they go to another 2 particles, okay? Here, it's a many-body system. So this means 2 particles that are in a Fermi sea. So basically they are holes in the Fermi sea interacting, okay? And then they are generating particles above the Fermi sea, okay? So this is the similar what you know, but in a many-body system, okay? Now, I will also, well, I don't know if I will say something, but the idea is, yes, I was saying actually, that if you have a particle, okay, that interacts with another one, okay, but now those are 2 particles in a many-body system, okay, and you close one of these lines, it means that this particle that is interacting with another particle in this Fermi sea, these closing lines mean that we are summing over all the other particles. So basically, the idea here will be that one particle sees all the other particles. Okay, this is what is called a is an F missing, self-energy diagram, which means or optical potential if you think non-relativistically. So this is the interaction of one particle as it sees the rest of them. So closing a line means summing over all the other particles, okay, of the other particles in the Fermi sea, okay? And now these diagrams that I was showing you here are diagrams of energy of the system, because what you are doing here, one particle sees the rest, and now I close this line. So that means I'm summing some over all the particles that see the other. So basically I'm summing over all the particles of the system. So I'm trying to find the energy of the system, okay? So this is the idea behind those diagrams. So those diagrams are energy diagrams, okay? And this is what you see here in what we want to calculate, the energy of the system, okay? Okay, I'm giving you fast, you know, or hints on many-body theory. So I hope at least you can get some idea. So now I'm showing you which kind of diagrams I'm talking about. I'm talking about these diagrams. I'm talking about, you know, the first one will be that one. Okay, so will be the fundamental state without interactions, interacting with this two-body interaction and going back to the fundamental state. Okay, so this is the first term here. Okay, you put n equals 0, and then you can forget about this, and you have the fundamental state with all the particles, and actually two of them interact with this two many-body interaction, and you end up with the initial. Okay, so you come back to the initial. The second one is this one, okay? So it's more complicated. So basically here you start from the fundamental, you end up in the fundamental, but you have something in between here, okay? Which is something propagating, okay? And these are all the other possible states that brings you from this fundamental state, two particles interacting through this two body, going to this excited, let's say, not fundamental state anymore, and then interacting back and going to the fundamental state. I will show you more detail, again, what it means physically, but let's concentrate on that one. On that one, actually, you can put it in terms of express it into terms of momenta, because you have translational invariance, so you can express this in plane waves. So this is for the one particle inside this many-body system. And this will look like that, okay? This is this term here. So basically, this is the Hartree fog that you know of, okay? Because if you, this H1 is the potential of two-body potential. So basically, you have here the Hartree, I guess you know a bit in electromagnetism, okay? Two particles with two momenta interacting and going back to the same ones, okay? And then two particles with different momenta and come back to, you know, changing the momenta, exchanging the momenta, okay? The difference here is that those momenta are inside, okay, the Fermi, inside this sea of nucleons, inside of sea of fermions, okay? And diagrammatically is these two terms here. How do you build these two terms? And now is this here. So the idea is to go to this interaction diagram. So you have two particles, okay, in the Fermi sea that interact and go actually to two others. But now what I'm saying you in the first order is that this I1 is I3 and I2 is I4. So what I'm saying is that basically I'm closing these lines because these are the same lines. And this is this firm that you're finding, okay? This is the Hartree contribution. The Fock diagram at first order is exchanging those. So I1 actually is not into I3 anymore, but I1 goes to the other one, I4, and I2 goes to I3. So basically you're having this funny, you know, closed diagram here. And this is these ones, the energy diagram associated to this first term here, okay? The second one is that one. And actually, it's a bit more tricky, but you can see, you can also understand it pretty well. So if you start, for example, with this Kj, this momenta of these two particles, initial, inside this Fermi sea, okay? And then you end up going to an AB, which are another two ones. So you promote, okay, into A and B. And then this AB momenta of these two particles end up in this, again, into this K and G, okay? This is this diagram here, okay? This is the idea of these skets here, okay? While this second one here, it's a bit tricky that you end up and finish in the same one, but then you have here an exchange, okay? So basically your initial K and G momenta, the K goes to A, as you can see here, that J goes to B, but then it turns out that here in the exiting ones, the B is correlated with K and the A with G, okay? So it's this cross term here, which in energy, it looks like this, because at the end you are summing over all the particles, okay? What it means, this diagram here, okay? So basically it means that you have a Fermi sea, a many-body system, okay? Which you have lots of particles occupying states, okay? Now, two of these particles inside this Fermi sea, okay, interact, okay? So this is this H1 here. They interact, and what happens? So by interacting, those are promoted above the Fermi sea. So these are these lines going up, okay, pointing direction up, A and B. And at the same time, you create two holes here, okay, which are C and D. So it means hole antiparticles, I don't know, in the Fermi sea. So holes in the Fermi sea, okay? And at the end of the day, those interact again, A and B, and you end up having the same situation as previously. But this interaction gives you some contribution to the energy of the system, okay? And this is why it's reflected by this diagram here, okay? So this diagram is the one that I was showing you, is one of the two that coming in this part here that is giving contribution to the energy of the system, okay? The interactions are giving you energy to the system. So you're moving from the fundamental without interactions. And now if you allow this, you end up, having more energy in the system, okay? By these interactions, okay? Do you follow me, more or less? So these are particles in the Fermi sea interacting, creating holes. So because of promoting above the Fermi sea, creating spaces in the Fermi sea, and then coming back, okay? This is the meaning of this diagram here, okay? Well, if not, I continue. And these are all the possibilities of all this Goldstone theory, all these possible diagrams that you can create, okay, if you do this expansion. So these are the hard tree at the first order. This is the hard tree at the second order. This is actually the hard tree at the Fox, sorry, at the second order. These three you saw, okay. Now you can also have, I'm assuming interaction of two body, okay. So you can also have three nucleons interacting, okay, but two body interactions. And you can have more complicated structures. So basically, for example, here, you had this one, it was like this hard tree in the second, sorry, hard tree, the direct diagram in the second order. But then you have a third particle interacting with one of the holes, okay? So all of these are possible, okay? Inside this expansion here, this infinite expansion, okay? These are all of them possible. Of course, the idea here is, I don't want to do an infinite expansion, right? I want to calculate the energy of my system. So I need to have some kind of systematicity or a way of knowing which diagrams are more important than the others. Otherwise, it makes no sense, right? I mean, because I just have this expansion, but at some point I want to calculate the energy of the system. So I have to see which diagrams are more important or not. Well, by looking at these diagrams, I already told you at the beginning that if you have the interaction, which is this V, which is indicated here, you cannot sum this diagram and then this diagram and then this diagram. So you cannot make an expansion just counting the lines of interaction, okay? So you cannot say that this diagram will be more important than this diagram because this has one and this has two lines, okay? This is not my parameter of expansion. My V is not my parameter of expansion. Why? Because of this repulsive character of the interaction at short distances, okay? So the idea then is to find a solution and to have a kind of a scheme in order to sum the right diagrams, okay? But how do you do that? And this is the basis of the Bruckner-Goldstone theory. So the idea is that if you have infinite systems, diagrams, to resum certain diagrams, okay, and do an expansion with the resummed solution, okay? How do we do that? Okay, so the idea again, the Bruckner-Goldstone theory is the solution is given by partially summing the most relevant terms up to infinity, okay? But how do we select? How do we select which ones to sum? Well, the idea is because of this dilute system. The idea is that we have a dilute system. So this was the range of the short range. And this is the distance between the two nucleons. And this is supposed to be small. And in terms of momenta, this means that, you know, the inverse of the distance is the energy. So this is the momenta. So the range A, which is the range of the short term interaction, times the momenta, the Fermi momenta, the last level occupied should be smaller than 1. And this is the condition that is fulfilled in this nuclear interaction because the short range repulsion. But what does this mean? This means that for each of these diagrams, you having a whole line, it means those that you know are pointing down here, it means summing, okay? Coming back, I'm summing over all particles, okay, that are inside this Fermi sea. So I'm summing over all these holes, okay? The idea is that each whole line implies an integral of a momentum up to kf, okay? This is what I was showing you. Well, each particle, these ones that are pointing upwards, okay, implies integrating above kf because you cannot go to already occupied states, okay? Remember, my C is filled up to kf, and then if you promote something, I mean, if you create a particle, it has to go above this Fermi energy, this Fermi level, okay? So the idea is that for this is what it means, and now it says, for low density systems, so kf small, in order to fulfill that, you have to have small kf. It means that the contribution of these line integrals with the whole line integrals is smaller than the contribution to the particle line integrals, okay? So if this condition is fulfilled, it means kf smalls. And if this is the case, then the contribution of those diagrams with whole lines, so it will be smaller than those with more particle lines. So basically the criterion here is the more holes you have, lines you have in a diagram, is the less important the diagram is, okay? For dilute systems. So this is the idea. The more whole lines there are, the more subdominant the diagram is for under this condition, okay? So here is already giving you an idea on how to classify these diagrams. It's telling you that those that have more lines pointing downwards are those that are most subdominant. So we have to look for those who have more lines pointing upwards, okay? And so this is one here. So diagrams are ordered according to the number of holes and not by the number of interactions. So the dominant diagrams in this expansion, in this perturbative expansion for energy, are those with less whole lines. And they form the ladder expansion. So what I'm saying is that I have to reshuffle them and put all those that have two whole lines. Okay, these are the basic ones, okay? Because this is the first ones in my expansion. So those that have two lines pointing down, this one, this one, this one, this one, this one, this one, and these ones. And this is, you know, lots of complicated, but you have one pointing down and one pointing down. So some of those diagrams will be the most important ones are here, okay? And the idea is to sum them all in order to create an effective interaction. And this is written down here, okay? Only showing the direct ones, but you have to imagine that you have to consider all of them, and you can end up, if you sum, for example, the direct ones, so you can see here, the difference is, you know, having, all of them have two whole lines pointing out, but you have lots of them with different interactions. So the idea is to create a ladder, so construct an effective interaction, which takes into account all of these diagrams, okay? And this is the interaction in matter, the one that I was telling you at the beginning that it was tamed, okay? With this interaction, okay, which takes into account the infinite sum of all the possible interactions, with this one, you can do an expansion, okay? And this is effective interaction of G matrix. The G matrix, the matrix comes because it's you think in terms of, you know, different momenta and you can create some matrices. It's not so relevant anymore, but the idea is this one. And I will stop here after that slide. So the idea is that you have to build your effective interaction. Now, instead of showing you energy diagrams where you had to close the lines, what I have been doing is this one. I have been summing all these diagrams in order to get my interaction, my effective interaction, my G matrix. You can see here how this works. You start with a potential and two particles interacting. I mean, two particles in the Fermi sea being promoted, okay? Now you have the same here for 3, 4, and 5 interactions, and you can see that it's repeating, okay? Now this expansion is repeating here. So actually you can express this like that. The effective interaction in matter at first order is the potential, plus now you have this G matrix again here, which is this resum matrix here, and the interaction here. So this is, in a formula, is this effective interaction in matter is the potential plus the potential times something that propagates, this two particle propagator here, which is shown here, and then the G again, the interaction itself. So you can see there is a non-transcendental, I think they're called equation, and where you have here the propagator of these two particles, you see the Pauli blocking, just to show you that we cannot go to momenta which are already occupied in the Fermi sea. So this is probably something you might have seen before, which is, and I will come later on, you know, similar to the T matrix, okay, or the Lippmann-Schwinger equation, okay, but in matter. Okay, I think I can stop here maybe for 5 minutes. Or 10.
Oh, okay. Is there any question for Laura?
Yeah, maybe a comment.
Yes.
Okay, go ahead.
The Lippmann-Schwinger equation is for scattering, while this one is for the bound state. So is like there is a correspondence between them.
Well, this is for the interaction of two particles in a medium, okay? And the other one, as you said, this is scattering in the medium. You know, if you want to put it in between quotation marks.
Mm-hmm.
So this is the, I mean, I was going to show you the similarities, okay? The similarity between the two equations a bit later on, okay? The difference comes in the propagation of the intermediate states, which have the information on the medium, okay? Which is not within the Lippmann-Schwinger is the free propagation, okay?
Okay. Thank you.
You don't see it. I was just showing.
No.
Sorry.
Yeah, maybe
I thought I was sharing.
If you put back here.
Yes, this one.
slide.
Sorry.
This
sorry,
one,
yeah,
yes,
yeah.
Laura. This one.
Yes,
Yes,
yes, this one. Sorry, I was thinking I was showing it. Yeah. So this is the Lippmann-Schwinger. Okay, where you have the propagation in free space of two virtual states. Okay. Here you will have also propagation, but you take into account that you're in a medium, okay? And then you have to take into account that you are Pauli blocked, so you cannot access states which are already occupied. And also the propagation actually in the energies of those systems also take into account the medium, okay?
Yeah.
But anyway, I will come back later on to this, okay?
In fact, as Laura said, the Bethe-Goldstone equation describes scattering in the nuclear medium. So it's the analogous to the Lippmann-Schwinger. And already if you have in the Lippmann-Schwinger an interaction with the hard core, you cannot stop at the first order, the Born's approximation. And you have to sum for nuclear-nuclear scattering in free space to all orders. And so to calculate the T matrix. In the medium, you have the extra complication that the scattering is in presence of other nucleons. And so you have the effect of the medium in the Pauli operator and also in the energy denominator, because you can also include a single particle potential that can be self-consistently evaluated.
Yeah, this I will mention later on. But
yeah, later on.
Yes.
So if there are no other questions, I think we can stop and make what, 10 minutes, Laura?
Yes,
or
we
less?
can make 10 minutes. It's okay.
10 minutes. Okay. See you later.
See ya.
Thank you.
We can, I guess, slowly start. Yeah.
Okay. Yes.
So I share again. Okay. So this is where I stopped before. So basically introducing you what this is, this effective interaction, this G matrix, and which kind actually of equation has to fulfill, which is this one, which is this Bethe-Goldstone equation. And again, as I was saying, I mean, you can see here that it comes from this expansion in potential, but the difference, and I will indicate again later, is this with the Liebman-Schwinger or the T matrix, is this operator here, this propagation in matter. Let's look at it into more detail. So the Pauli blocking is what I'm repeating all the time. You know, it means that it only allows these two particles above the Fermi level, the last occupy momenta in this sea of nucleons. So it only allows two particles above that value in the intermediate states. And again, well, this is called the Pauli operator. And yeah, well, this is just to indicate what it means. Regarding the energy denominator, well, the idea is also that that this is the energy of the fundamental state without correlations, and H0 is the free Hamiltonian acting on the intermediate state, in this case, two particles, two holes. So if you apply this, for example, to a state of two particles and two holes, you get energy of the fundamental state minus the energy, then you get this H0 being applied on top of this. So basically it means the energy of the fundamental state plus the changes in energy of this two particle and two hole. So you have the energy of the two particles minus the energy of the two holes. And then, well, the energy of the fundamental state is canceled. So you end up here having here the energy of the one hole and the other one minus the energy of the the particle one and particle two. And actually this one is called the starting energy. So it's actually a parameter, an energy that is already telling me, you know, showing me that this G matrix will depend on an initial energy that you are starting with. So this is kind of a parameter. It's different from the Liebman-Schwinger. So again, the equation now you have is the sum of the first term is the potential times the potential, and then you have the propagator, which this sketch here indicates this Pauli blocking, okay? And then the propagation of the two particles, the momenta has to be above the last occupied state, okay? And this energy, which is what is called the starting energy or the initial energy, okay? So what is the analogy? And now again, what I was mentioning before with what we know in scattering in free space. So Bruckner, you know, found that the G matrix could be interpreted as describing the collision of two particles in the presence of a medium. So there is a parallelism with the Liebman-Schwinger equation that for two free particles, which is given here. Okay, so the expansion in potential. So the first term, as Ignacio said, this is a Born approximation, which, sorry. And this propagator here of these two particles that are in free space. However, the most important difference is this Pauli operator. Okay, so the idea that indicates that the two nucleons interact in the presence of the other nucleus, and therefore there are occupied states that are not accessible, that you cannot scatter in medium because they are already occupied. Okay, there is also difference in the energy. Okay, but the most important one is the fact that you have fermions and you cannot scatter particles in the medium to states which are already occupied. Okay, so this is the Pauli operator. And as you see, you know, there is this parallelism, and the difference again, it comes through this propagation of particles, that before there were two free particles, and now there are two particles in a medium. Okay, good. Now we know the G matrix. We have resumed partially certain diagrams. Okay, this is what we have done. We have replaced the potential by this G or effective interaction, which is well behaved. And now we have now an infinite sum of diagrams, which are result, each of the diagrams of a partial resummation. Okay, so this is what is written here. This suggests to convert each potential interaction into a G matrix line by summing the proper sequence of ladder diagrams, avoiding, of course, double counting. And this is called the Bruckner-Goldstone expansion, okay, in which of the terms, any of these terms is well-behaved and finite, okay? So you have, remembering all these diagrams here and more, okay? Now you have resummed some of them in such a way that you end up having all these diagrams, and of course many more, infinite of them, okay? But when you have substituted this interaction, the wiggle interaction by this, wiggle line, okay? This dotted interaction by the wiggle continuous line, okay? Now you will have again infinite, okay? You will have lots of diagrams with this wiggle line that are well behaved, which is was our goal. But of course now the question is, how do I do a proper, calculation? So how do I do my perturbation theory? Okay, so I know that those are well behaved, but which ones are the most important ones? Okay, so because I need to stop at some point, I cannot resum infinitely. So the solution actually was given by, it's written here, Bruckner, Goldstone, and Gammel, which is based on the whole line expansion. So this is not a theorem, it's just you do it and you see, actually. So actually, those diagrams which have these whole lines, okay, these lines pointing down again, are more important than those who have one line more. So again, the importance here comes because of being a dilute system, okay? So going again, recapitulating or summarizing, you had an infinite series where you had all potential diagrams with an interaction given by this potential. But this was impossible to determine an expansion in terms of the potential because there was this bad behave at short distances. Now we have found a new series, which now instead of having the potential, you have a effective nucleon-nucleon interaction. Instead of having the nucleon-nucleon interaction, you have the effective nucleon-nucleon interaction that takes into account that you are propagating in a medium. And this has helped to have all these terms which are finite and well-behaved, okay? But of course, now the point was, but which ones are the most important, okay? Because I don't want to sum them all. And the idea again, it's based on the fact that those that have more lines, more whole lines, more lines pointing downwards are those that are less important, okay? Again, this is not a theory. And the idea behind that is that if you interact two particles, they jump to states, excited states, and they come back to the same two initial states, is more the probability of physically, that this happens, is more probable that you interact two, and then there is a third one that interacts with one of them, and then reinteracts again and goes back. So basically the idea is that the less, I mean, this is physically the idea, but again, the idea here is you have a dilute system, so the less whole lines you have is the ones that are more dominant, okay? And you learn that by doing, okay? So basically, this is what is called the whole line expansion. So you have to classify all those diagrams in terms of the whole lines they have, okay? Okay, so, yes.
Laura, sorry.
Yes, tell me.
Laura,
yes.
From an historical point of view, if I remember correctly, it was Hans Bethe and mainly his student, Indian student, Rajaraman, who demonstrated that you have to resum the diagrams according to the all number of holes, what is called all line expansion. This was Rajaraman in 1963, something like that. But maybe I'm wrong, but it's my memory.
I thought it was Bruckner, Goldstone, Gammel, but okay, if you we
in
can
fact,
just look it up,
in fact, it's called also the line expansion is called Bethe, Bruckner beta Goldstone
Yes.
expansion.
Yes,
the online.
exactly.
Okay.
Yes, yes.
But just
yes. Okay, thank you.
Okay.
Okay, so which is the lowest order? So the one that has less whole lines, okay, as we say. So this is actually the Bruckner-Hartree-Fock. Okay, why? Because this is ones. You take into account those that have two whole lines, okay? And this is the Hartree and this is the Fock term, okay? And why is it called Bruckner? Because always this Bruckner, okay, Bruckner-Goldstone theory, okay? So in this is the diagrammatic form, okay? In terms of putting it in terms of momenta, and you can see here that you have, this kinetic term. I mean, this is the energy of the system without not perturbed, okay? So you have all part, I mean, this momentum, the energy, the kinetic energy, and summing over all the particles that have this momenta below the maximum level, the Fermi level, okay? And then you have the Hartree-Fock. So this is the Hartree and this is the Fock terms, where you have now the interaction, which is this effective interaction, which depends on the energy, okay, of these particles here. Well, on the holes and the starting energy. So basically it's the energy, okay, inside the Fermi sea, okay? And this interaction, this effective interaction, it's indicated here, is this, you have to find it through the Bethe-Goldstone equation, okay? So you have, it's an equation where you have the potential times the potential times the propagator and then the effective interaction, okay? And then you see here the energies, okay, of the particles which are propagating above KF, which are P and L, and those are the ones inside the Fermi, that are the holes, okay, in the Fermi sea. And the idea is, of course, I mean, that you have to, in order to calculate the energy of the system, you have to know your effective interaction, and then in the effective interaction, you have to solve this. Now I will show you, kind of the algorithm of how to solve this, okay? But in any case, just that I was saying, this is the Bruckner-Hartree-Fock, which is this approximation. This is the lowest order. And it's analogy with the Hartree-Fock that you all have known. But here the difference, of course, is that the potential has been substituted by the G matrix, okay, by this effective interaction in matter. So what is the algorithm, okay, in order to get, finally what you want is the energy of the system in this approach, okay? So what do you do? So you start with your trying to solve the Bethe-Goldstone equation, okay? So the idea is that you start so for a single particle spectrum. So basically you assume, the first step is to assume free energies, okay, for the particles that are being in this medium, okay? You don't know, but this is how you start, okay? And then you plug in your energies, and then you solve this equation. This is possible. Is this possible to solve? Okay, you can do, there are different ways of solving this in order to get your interaction. Okay, now you calculate. Now, of course, you know that the particles in this medium are modified, okay, because of this medium, because one particle sees the rest. So there is an information, this self energy, this potential that feels because of the rest of the others. Okay. So then the idea is, with this interaction, you compute the single particle potential. So basically is summing, so one particle sees with a certain momentum m, sees the rests, which are this indicated by this G momentum, and you sum up over all this Fermi sea, okay, all these occupied momenta. With that, now you can sum the energy, the kinetic part, and then you get the new single particle spectrum, okay? So you get the new energy of the particle, okay? Because now you know the energy that feels in this in this medium, okay? And now, of course, this energy was different, the single particle that the one you plug in, okay, in order to compute the interaction in matter. Okay, so these denominators before it was free particles. You imagine like the free Fermi gas, okay, or like I like Fermi, you know, like the relativistic energy, momentum squared plus mass squared, square root of everything. Okay, but now you've seen that through that you get the new energy. So the idea is to plug that in the denominators, okay, and do again and find this, the effective interaction in matter. Now you compute again the single particle potential, you go and calculate the energy. And now you compare whether the energy, the single particle energy of each of the particles is the same that you were plugging in order to compute your effective interaction. So this is what I mean by self-consistent calculation, okay? So you have an interaction, effective interaction that depends on the energy of the particles that are being propagated, okay? And therefore you need to know them in order to know the interaction, but you need the interaction in order to know the effective, the energy of each of the particles. So therefore is this self-consistent calculation that you have to do, okay? And once this is reached, once you see that what you plug inside is the same as what you get out, then when the self-consistency is reached, then you can now get the energy of your system, because now you know the energy of each of the single particles that form your sea of particles, and the idea is to sum over all those particles in order to get the energy of the system. Okay, so this is kind of, you know, in few words, the idea on how to solve and how to find the energy of the system using the lowest order term in the Bruckner expansion, which is this Bruckner-Hartree fog. So again, I mean, if you know a bit of scattering, I mean, well, maybe better not. It's just that you have to have this self-consistency, because the effective interaction depends on the energy of the particles that are interacting, okay, because of the medium. And therefore, you have to do this self-consistent in such a way that at the end you have the energy and you sum over all the energy of all the particles that are in your Fermi sea, and you get the energy of the system, okay? You follow me? Or you're totally lost? Well, if not, ask me questions at the end. So this will be, you know, the philosophy. Now we put hyperons, okay? Now we go in hyperons. Now we complicate a bit our lives. Why? Because you will see there is what is called the coupled channel structure. So this could be a summary for the nucleon, okay, that I was showing you. So you have your effective interaction, then you compute your single particle energy and single particle potential. So this is the potential and then the energy. And then you sum over the energies of all the nucleons and you get the energy density, okay? Okay, this was for one nucleon, but nucleon. But now I'm thinking about hyperons, okay? I'm thinking about interaction of lambda nucleon, for example, going to lambda nucleon, or lambda nucleon going to sigma nucleon, which is possible because the quantum numbers of those states are the same, okay? So in this way, this is why all these sums here over BA5 and B6, it means the different baryons which have the same quantum numbers, okay? So for example, in order the effective interaction of a particle baryon 1 with baryon 2 going to baryon 3 and baryon 4, you need in the interaction, in the propagation, to also take into account that you might have two baryons, 5 and 6, which are not any of these 4 ones. This is only possible, of course, if they have the same quantum numbers, in the sense that the strong interaction conserves this baryon number, conserves also strangeness, conserves certain quantum numbers, okay? But this gets a bit more complicated because you don't have anymore only nucleon, but you have, if you want hyperon nucleon, lambda nucleon, but then you will have to think about sigma nucleon, for example, okay? But the idea is the same, only that your, let's say, space has been increased, okay? So, but then this is the idea the same, you need this interaction, and therefore you have to, for example, for obtaining the potential of one baryon, you have to take into account all baryons and all their Fermi seas. There's not only one sea of nucleons now, but it might be that if you want the interaction of a lambda with a nucleon, you also have to consider the interaction, as I said, the sigma nucleon. And also, for example, if there's sigmas, which probably there's not so many, you will also have to take into account. So you have to take into account all baryons that are also into the game, okay? In order to get your energy and then do this self-consistent approach again. And finally, the energy of the system is summing over all baryons, all their energies, okay? So what I'm more clearly, this is what I meant by self-consistency in coupled channels. Let's look at nucleon-nucleon, okay? So here I'm working what is called in the coupled channel basis, okay, in the isospin basis, basically. The idea is to get all particle, for example, nucleon, no, neutron, proton, neutron, that can give you, because of the isospin projection, can give you isospin 0, total isospin 0, or total isospin 1, okay? You know that the nucleon and proton have isospin 1/2, okay? And the third projection is -1/2 and 1/2. So basically, you can combine neutrons and protons in isospin 0 and isospin 1, right? You know that this system doesn't have any strangeness, okay? So you see that the only possibility conserving quantum numbers of isospin 0 and strangeness equals 0 would be nucleon going to nucleon. And if you consider isospin 1, you will have the same, okay? But now, if you have strangeness, if you have hyperons into the game, in order to, for example, let's look at strangeness -1. When you have lambdas, when you have sigmas that have strangeness -1, you can see that in order to compute the lambda nucleon going to lambda nucleon, also lambdas and nucleons can interact with sigma nucleons, okay? And it's also, let's say, in the same box, sigma nucleon going to sigma nucleon. So the idea is that all this system has a strangeness -1, and now it will have isospin 1/2 because, for example, the lambda has isospin 0, okay? So if you combine lambda and nucleon, you will have isospin 1/2. Of course, the sigma is the spin of the isospin of the sigma, okay, is 1, and therefore you can also have it in other situations, like here, for example, in isospin 3/2, but then you see that's the only system that has a strangeness -1 and isospin 3/2. So I mean, with the idea here is that when you have hyperons into the game and you want to compute any interaction involving hyperons or sigmas with nucleons, or lambdas with lambdas or sigmas with lambdas, you have to be careful that all of them, you know, participate or will influence the other ones, okay? Also, strangeness -2. You can have all these systems with the same strangeness and isospin 0. So in order to study the lambda-lambda interaction, you have to be careful and also study the cascade nucleon, for example, okay? So this, you know, gets more and more complicated, but it's just a matter of being careful and taking into account all the particles with the strangeness that you think you can have there, and take into account how they will influence one to the other in the calculation at the end of the effective interaction in matter and the total energy density. Okay. Well, with that, I stop about theory, okay? So I just wanted to show you, as I was saying, a way of calculating the energy of the system, okay? And this is this Bruckner-Hartree-Fock, which is one of the ways that people usually work in order to get this energy of the system. Again, there are also ways, other different manners, you know, this density dependent, people who have worked in relativistic mean fields, it's another way of approaching the same problem. The only thing in this Bruckner is, of course, that you need a starting potential, a two-body potential. And this is what I was explaining you in the first lecture, okay? I was explaining you different ways of building the hypernucleon interaction, okay? Mainly I discussed hypernucleon, lambda nucleon, sigma nucleon, cascade nucleon, okay? And one of the ways, well, the two ways that I mentioned, it was meson exchange models and also these chiral effective theories. So here I'm just showing you examples of recent calculations. You see, I'm talking about like 5-6 years ago on this new pretty new, as compared with meson exchange models of effective field theories, okay? So now I know how to compute my effective interaction. Now I want to calculate the energy of the system. So I need an interaction as a basis. I need my initial potential, my two-body interaction. And this is done in those examples with the meson exchange model and these effective theories, okay? So the diagrams are those. I mean, this is Bruckner-Hartree-Fock, okay? It's the same diagrams, but for the potential, the self-energy, or the optical potential in the non-relativistic version. And this is what is plotted here, okay? The optical potential of a lambda in the presence actually of a nucleon C, okay? Mainly here, you think of the nucleons are the most abundant one, and this is actually the case. And you try to compute first the potential, and of course, then the energy per particle, the energy density, the energy per particle, the equation of state, okay? So examples. So I'm talking here about lambda and sigmas in dense matter. These are this effective theory, a leading order and next to leading order. And now these are the results of this potential, which is these diagrams here. So this is the lambda, for example, in the presence of a sea of nucleons, and this is the effective interaction in matter. Or again, the lambda in the presence of the nucleons, but this is the Fock term, okay? And you see here values for, it means zero momenta, okay, and saturation density at KF 1.35. This is this value I was telling you that is about 0.17. And you see values, this is a cutoff because this calculation requires some parameters that are kind of free parameter, but some reasonable values are expected. So for cutting the integrals, these are called the cutoffs. So you observe values in this model, a leading order of around -38 to -34. While when you add up next to leading order, these values are reduced, okay? This is plotted here. This is a band, a leading order, and this is the next to leading order. So, and you see that at this KF of 135, which is saturation density, we should be somewhere here. Okay, around here. This is the difference between these two calculations, let's say, including higher order corrections, okay? And well, as I was mentioning when I discussed hypernuclei, this is not so bad, okay? Because it's giving you binding energies of around 30 MeV. This is what we expect. So it's not so bad, actually, for what we would expect for the lambdas. The sigmas, as I was telling you, here is more controversy, whether there's repulsion, whether there's attraction. It seems it's going to be repulsion at densities of this saturation density, at this density of that we were discussing. And in particular, in this case, in this model, actually, this depends on some partial wave. Maybe we don't have to go into these details. It's just that this is decisive in nuclear matter, and the results, assuming some repulsion in this partial wave, will give you this potential of repulsive potential at saturation density, which is a KF of 1.35. So we are talking about here, okay? Again, this is the next to leading order, and this is the leading order, okay? So these are examples for effective field theories for the calculation of infinite nuclear matter using this Bruckner-Hartree-Fock approach for computing the medium interaction of particles, okay? You also see, it's difficult to see it, actually here it is not, the Jülich model, which is this meson exchange, and the difference between these more recent calculations. And again, this is always the issue, you know, of the parameters and some of the freedom that we have in this basic interaction, okay? The many-body scheme is Bruckner-Hartree-Fock. The difference here is the starting interaction, okay? And the starting interaction, it has some parameters, and those are not well constrained yet. And they have to be constrained by experimental data, and the data is also not so good yet. Okay, this will be for lambda sigma. Also, something more you know about the lambda sigma. Here are calculations of the real and the imaginary part. Before I was just showing you at zero momenta and the real part. Okay, here is as a function of the momenta, the real and now imaginary part, also to show you that there are decay possibilities. The imaginary part in the optical potential or the self-energy indicates possibilities of decay. Okay, so there is also possibilities that you see at larger densities. So the imaginary part is different from zero. And then, well, the results, okay, with these effective field theories. And also here you find two models for the meson exchange. So you can see here, there is a difference. Momentum depends on these potentials, depending if you look at or leading order or next to leading order or some meson exchange model. So again, here, the many body framework is the same, but the basic interaction, the potential is different. Okay, and the differences arise because there is not much information on scattering, and also we only have as well few information on hypernuclei. Okay, this is for the lambdas, and now this is for the sigmas, just to show you, for example, the sigmas, this repulsive behavior as compared to the lambdas for low momenta. And also here, this is symmetric nuclear matter. This is what I was telling you all the time. Nuclear matter, the same number of protons and neutrons. So I assume an infinite system of the same number of protons and neutrons. If you now locate yourself and think more neutrons than protons, then there arises differences, particular in this, what is called the isospin dependence on the interaction. And here you see the lambda sigmas, the three sigmas, and the lambda and the three sigmas. In this case, down here for different densities as a function. These are different, proton fractions. So this is neutron matter, and this is, different, so proton fraction 0, and here will be different proton fractions as a function of the total density. So for example, if we look here at different Fermi momenta, so that means different densities, you will have a different momentum dependence of all these different particles. And here, as I said, now is not neutron matter, I thought it was. It is for different proton fractions, okay? And then you also see different behavior of the different particle densities. These are just examples, okay? The details is not necessarily that you understand, it's just that you know that now the Bruckner scheme is the same, and you can compute in the potentials, the self-energies, okay? All of this information, for example, you can find in this recent, 5 years, 6 years old paper of people working on that, okay? I was talking now about lambdas and sigmas, but of course there's also cascades that we also discussed when talking about hypernuclei. So they have these two strange quarks. Here, the situation, experimental situation, is even worse, okay? For the lambdas, we had these hypernuclei, so we had several of them. For the sigma, it was this discussion, repulsion, attraction. Now for this one, there is very little information. Actually, there's basically some kind of upper bounds on the cross sections. So you see here how the different models do a basic model, effective, these are not models, this is based on effective field theory. Then this, let's see, this is the next to leading order, the red one is next to leading order. And I think the difference between this line and this line is because there are some parameters that are not so well constrained, and you have some freedom in order to, next to leading order parameters, to constrain them. So you can see here discrepancies, of course. And actually these are cross sections for different systems, cascade minus cascade minus interacting with proton and going to cascade minus proton. This is cascade 0 going to neutron, and then some others, cascade minus proton going to lambda lambda, cascade neutron sigma 0 lambda, so they have the same quantum numbers. This is also this coupled structure I was mentioning. And now how this ends up, in looking, in the medium. And you see here the kind of discrepancy, okay, even in the what is supposed to be a correction, the next to leading order on top of the next to leading order on top of the leading order. And this is again because there are different assumptions, and this is not really you would not expect that this is that the next to leading order here comes as a perturbation on top of the leading order, because there are different assumptions because of the freedom that we still have in some of the parameters, okay? In this one, it's also shown, for this is a meson exchange model of the Nijmegen group. And this, I believe, is a kind of a quark model description. I'm not so sure about this one here, but just that to indicate you that if we believe the next to leading order is going in the right direction, which we have to take in quotation marks because, these discrepancies here with the leading order, you would say that we're having an attraction of around what? Actually, between -3, -5, around the saturation density will be here at this KF. So we have a moderate attraction, but we also having some information experimentally. And one of the most recent one is -24 MeV. So you can see here that we are still not able to describe actually this experimental -24 of the cascade attraction. It goes in the direction of other Bruckner-Hartree fog with other phenomenological potentials, but still there is a bit of, not consistency with experimental data, okay? So you would say, okay, when this is not so nice, well, but there's also a lot of space to improve things and to work and to investigate, okay? So it's also not to get the negative part of that, but just, we are having some issue here, we have to solve. Actually, what's the main point here is what actually the interaction is, okay, between the cascades and the nucleons, which is also something that is not so well known, okay, because of the experimental data we have. Okay, this is actually for that. And actually, I have been going too fast, but I think people will be happy if this is actually my last slide. On lambda in this matter, and coming back to the Hyperon puzzle, I mentioned on Monday that, it seems that hyperons are energetically probable in neutron stars, right? But then if we put them, the equation of state will go softer, softer than in the case of only nucleons. So, but in this case, this will mean that the pressure of the system, is less than before. And if the pressure is less, then it could be difficult to obtain, these two solar mass observations, because you don't need such a mass to compensate, gravity, the pull of gravity it doesn't have to be so strong. So you don't need so much mass in order to compensate the pressure of the particles that are inside, okay? And there are different ways of solving this. I mentioned, basically the idea is to push hyperons to appear late, okay, in the star. In this way, you will not make it soft so fast, okay, and you could still reach the two solar masses. So one of the ways, and actually Ignacio mentioned it, is this inclusion of the three body force involving hyperons, okay, to have some stiff interaction that helps, to make actually the equation of state stiffer, and basically also making less favorable to have hyperons. And this is the case that, for example, these people have investigated, the group, this is the group of Bonn, Jülich, that they have created all these interactions. They have created this three-body interaction, which into the Bruckner-Hartree fog is implemented through the two-body density dependent. These are the diagrams for having this two-body density dependent interaction involving hyperons. And one of the things, that they have observed using this is how the chemical potential of the lambda behaves with compared with a neutron. You remember that I told you in order to lambdas to appear, the chemical potential of the lambda has to be smaller at some point has to be equal to the neutron. And if it's smaller, then it's more favorable to have lambdas than to have neutrons. So this is the case here. Actually, by doing that, it turns out that if you include these three body forces, okay, with this lambda nucleon, then the chemical potential of the lambda is always larger than the chemical potential of the neutron, okay? And in this case, you're basically not able to produce these lambdas, okay? And therefore, the equation of state will be still stiff and you will not have this problem with the hyperons, okay? So somehow this solution here is, okay, lambda hyperons will not appear, okay? Because you have the three body forces and therefore you don't have the issue, okay? Well, this is one way, you know, that they are solving this. This is with one version of the next to leading order of the 2013. The same they observed for the 2019. So basically here, as I said, you know, they improved in the interaction, they created this three body, and basically this three body interaction as they are using it in here is not allowing to lambdas to appear. So if lambdas do not appear, then of course, I mean, the whole thing doesn't get soft, and then you don't have the problem of the hyperon fuzzle, right? But as I said, there are different ways, and of course, there are different also interactions that are being used. Three body, not so many in the effective theory, but the others, and then this solution, you know, is a possibility, okay? It's not the definitely solution, I would say, because also it's possible to make the interactions to body more stiff, or even not push the appearance of hyperons as this is doing, but this is doing it by not appearing them at all. This is also possible to have them there, but appear late because something else is happening, like other deltas or, you know, or condensates. Also, you have to be careful, because if another thing appears like deltas, this will also soften the equation of state. So, you know, you have to see whether within a reasonable scenario, this can help you to solve this hyperon puzzle in neutron stars, okay? But anyway, just I wanted to show you how to connect, okay? This all this theory I mentioned of the Bruckner-Hartree fog to try to connect to computation of potentials of chemical potential in this case, okay, and how to connect, for example, with the neutron stars that we discussed the first day, okay. So here you have some of the information. That is also the bibliography that I used in order to explain all of this. I mean, for this lecture. And yeah, now I think we have some time. I think like what, 5-10 minutes for questions. So also maybe to relax before the other lecture starts.
Okay, thank you very much, Laura. And is there any question, comment to the Laura lecture?
Yes, hello.
Yes, hi.
Go ahead.
Hi. I have a question about the hypernuclei. When you change a proton by a sigma plus or sigma minus, is it change the nature of the nuclei, like changing the carbon to the Bohr or something like that?
You have to be in, what I was showing is lambdas. So lambdas, you know, are substituting neutrons, and then for example, here is changing. Okay, you can see so it depends on the reaction. In that case, it was not actually. So here we were substituting a new.
Laura.
Yes, tell me.
Could you share the screen?
Yeah. Sorry.
It seems that you are commenting some
I always think I'm sharing, and I'm just not
okay.
sharing.
Thank you.
Sorry. What I was saying, yes and no. What I'm saying is depending on the reaction. For example, on that one, you have a neutron that substitutes. Sorry, a lambda that substitutes a neutron. Okay, so you're not changing. Okay, the nuclei. But on that one here, yes. Okay, you can see here that I'm moving for carbon to Bohr, right? B is Bohr. So you are changing it, okay? Because actually you are somehow involving a proton in the game, okay? So yes, it can happen that the nuclei is changed, yes.
Maybe I would like to, if you could say just a few words about, say, the convergence of the whole line on the one hand. On the other hand, say, comment about maybe the possibility of using other many-body scheme that are also fashionable to do. I mean, just today, no, based on ab initio, chiral theory. I mean, just a comment that allows us to to see things in perspective.
Well, the first thing you were asking me about the whole line expansion, right?
Yeah, the convergence. I mean,
the convergence of the whole line. Well, the convergence is just doing it by hand. Okay, this is a bit maybe it's disappointing for people which are which love to have a really careful perturbation theory that probably in effective theories, I mean, you have. But here, you know, it's, as I said, this is not a theorem. So basically, you find, okay, that when you go to diagrams with not 2 whole lines but 3 lines, the contribution is smaller. But this is very also complicated and calculate. Okay, it involves many diagrams, so it's also very difficult, you know, to. So I cannot give you like a percentage if this is a question you're asking me. Okay. So just that you stop there, and then some people have gone to, you know, to in this whole line expansion to look at the 3 lines and so on. Okay, but yeah, I cannot give you a percentage if yours was the question. Now about the other questions about other ab initio, for example, if I had the slide, but okay, there are. For example, quantum Monte Carlo methods. Okay, so basically you put. I mean, I'm not too familiar. Okay, but you put them into or lattice. Okay, so you just put it into for example, lattice, and then you just try to. But lattice is complicated. Maybe better quantum Monte Carlo. So basically, you do some simulations, as you know, with these hyperons into the game. Or also, for example, these are more familiar renormalization group methods. Okay, that people have done. The idea of the renormalization group methods is to integrate out the larger components, okay, and put the information into the constants, into the coupling constants. Basically, you have some renormalization equations that integrates out these high energy scales, and this has been very successful. For example, for nucleon. Why? Because at the end of the day, all these nucleon interactions, even if they are very different when short distances, because of this uncontrolled, okay, interaction at short distances, when you integrate out this, you end up having what they are called a universal potential, okay, that can therefore do some perturbation theory. Okay, so somehow this method of renormalization group, the idea is to have a potential, a two-body potential that is tractable, that forgets about the short range part, forgets about in the same that integrates it out. Okay, so in this way you can do perturbation theory. So you are somehow integrating out this part that is giving you the many body problem, let's say. Okay, so this is a few words, for example, on this renormalization group. The quantum Monte Carlo, I didn't give you details because I'm not an expert. And these are, for example, ab initio. There is also then density dependent approaches, density functionals. So ones that I'm familiar with are relativistic mean fields. Okay, so those are based on the idea, for example, I was showing you before, nucleon-nucleon interaction, that the interaction is mediated by the exchange of some mesons, in particular the sigma, the omega, and if you go to neutron stars, the rho, because this gives you this isospin breaking, okay? And the idea is that you do some mean field approximation in the sense that you have your equations of motion, and then you have equations of motion for these fields that are the interaction, plus of course equation for the nucleons, which are the ones that are interacting. Okay, and then you get your equation of state. I mean, they are very also from density dependent or functional dependence. There are also statistical methods There is also Thomas Fermi, which assumes some, I don't know, local density, Fermi distributions at certain points. I mean, there are very different ways, okay? So I just wanted to show you, I don't know, this will give you a different lecture for each of the methods, sorry.
Of course, just to have a short landscape, no?
Yeah, this is the, yes.
Yes, thank you.
Yeah, I mean, if you want to have a short landscape, just the names, I just go to the neutron star lecture that I did like on Monday, and then you will find the names and the authors.
Okay, thank you. I want to add a comment to the question that Enrico raised about the convergence of the online expansion. So this is a very long-standing problem, Enrico. And the first person who calculated the contribution of the three-line expansion, it was Ben Day in 1970s with the gap choice for the for the single particle potential. Yeah. And later Mao in the 80s demonstrated that using the continuous choice, the convergence of the online expansion is much faster. And this was numerically demonstrated, I think, in the 90s by Marcello Baldo, Umberto Lombardo with the Chinese Song et al. They calculated the three-line contribution with the continuous choice for the single particle potential, and they numerically demonstrated that the convergence is fast. So the three-line contribution, at least up to, let's say, twice, 3 times the saturation density, are small compared to the two-line contribution. And I think, since I am also the chairman of this session, that if I don't see any other question in the chat, we can thank, first of all, Laura for this lecture. And now I make